Hello, everyone. My name is Harish Vedantam. I'm a scientist, astronomer working at Astron, the Dutch Institute for Radio Astronomy. And through a series of videos, I would like to teach you introduction to interferometry as used in radio astronomy. This is the first of those lectures. So first up, I just wanted to let everyone know that the prerequisites to understand the material that's going to come in these lectures are given here. So I would assume a basic idea of Fourier transforms and of complex analysis. So by complex analysis, I mean just some familiarity with complex numbers, complex representation. So you should have heard of something like e to the power of I omega t, for example, a complex representation of a sinusoid. Some basics of electromagnetic field theory. So I would assume that you would be comfortable with electric fields, magnetic fields, flux densities, things like that. And some very basic algebra and calculus, which you would have learned in either high school or first year of college. Okay, so with that, let's get started. So the first thing I want to discuss is the idea of what I call an aperture. So an aperture is basically some kind of area over which you measure the electric field of astronomical sources. So let's start with the simplest one, which is a point-like aperture. So you can think of having a tiny detector, which is just measuring the electric field fluctuations which fall on the Earth, where the detector is because of a large number of astronomical sources. So I've drawn 5 sources here. These sources are at very large distances, so the wavefronts coming from these sources are going to be plane waves. You can think of it as the limiting case of a spherical wave when the radius reaches infinity. So you're not really going to be sensitive to the curvature of the wavefronts. It'll look to you as if it's a plane wave. And so if you have a detector, each source creates a random electric field which falls on the detector, and what your detector will measure is simply the sum total of all the electric fields. Now that's good enough if you simply want to know the total power that's falling on the detector from the sky. But in most cases in astronomy, that's not good enough because we want to have some angular resolution. So we want to know what is the power, the radio power coming from, let's say, source one. And so we need a way to exclude the electric field of source two. And so the way we have to do that is by having a larger aperture. A point aperture is not going to lead to a discrimination between power coming from different directions on the sky. And so let's take the next simplest example of an extended aperture, which is just having 2-point detectors on the sky. So now you have a spatial extent in your detector. And so I'm going to now show that that leads to a basic discrimination of angle of arrival of radio waves which are falling on the detector. So let's take a simple one-dimensional case, or sorry, two-dimensional case, where you have a detector on the x-axis at x equal to 0. You have another detector measuring the electric field at x equal to a. And let's suppose that there is some source which has plane waves coming where the wavefronts are making an angle theta with the zenith, as I've shown in this figure. And so the first detector at x equal to 0 at some time t is going to measure some electric field. But because of the geometry of these wavefronts falling on these two detectors, the wavefronts are going to arrive first at x equal to a, and the same wavefront is going to arrive at x equal to 0 after some delay, right? And so that delay depends on the extra path length that the wavefront has to travel, and of course the speed of light. And so what you measure at x equal to a, this detector is just a delayed version of what you would measure at what you measure at x equal to 0 is a delayed version of what you would measure at x equal to a. So you're going to get the electric field something like this. The electric field at x equal to 0 is just the electric field at x equal to a, but of course at a time which is different by this factor. So let's say a is the distance between the detectors, a sine theta is the projected distance, which is what matters here, and c is the speed of light, right? And so this is just the extra time delay that one needs to account for. Now, let's suppose that the waves which are coming from this source are monochromatic. So let's suppose that the waves, you're interested in waves at some frequency omega. So omega here is the angular frequency. And so if I try to write the same equation here, but for a monochromatic wave with frequency omega, then I can write something like this. So instead of a time delay, I'm just going to write this as a complex phase, which I need to account for when the wave comes to x equal to 0 by traveling the extra path length, right? And so that delay is basically converted to a phase for a monochromatic wave. And that's just a complex notation of that phase. Now, if I'm interested in the electric field of this particular source, which is at this angle theta, all I have to do is I need to undo this delay or phase. So in my once I get the electric fields at these two locations, I'm just going to add them, but I'm just going to undo the extra delay. And I would do something like this. So I'm going to take the electric field at x equal to 0 and then add the conjugate of this. So that would be equivalent to delaying this. But of course, you're delaying this not in the physical world. You have recorded the electric fields and you're delaying it electronically, so to say. But the effect is the same. It is as if these two waves have been added with the delay taken into account. And so that would be what you would run your detector on. You would add these two with the right delays, and that is basically what we call beamforming. And so beamforming is just a way to add the electric fields that fall on different parts of the ground with the correct delays, such that a signal which you're interested in coming from some direction adds coherently, as in it all of the signals are going to add in phase. And that's what basically beamforming means. And so what you're essentially doing here is you're coherently adding signals from the direction you're interested in, but for other directions, these delay terms are different. So you would not add them coherently. You're going to add them with phases which actually don't correspond to the delays. And so their electric fields are going to slowly average down to 0. The more detectors you have here, the more random phases you're going to add the electric fields of the other sources, and slowly they're going to average down to 0. And that's the essential sense of beamforming. Now, in practice, the most common way you would have probably encountered beamforming is with a dish. You would have seen probably dish antennas used in various applications. And a dish is basically doing just that. So what it's doing is, let's suppose we have a dish and it's pointed at some direction. The dish basically has this surface which has a special geometry. It's a paraboloid, and the speciality of this geometry is that for any electromagnetic waves coming from this direction, which we call boresight, all the reflected rays, when they interfere here at the feed horn where you put your detector, they all interfere in phase, right? So they all interfere coherently. And for wavefronts coming from any other direction, they are not going to get reflected and then interfere coherently. And that is basically the definition of the geometry of this dish. That's what you basically do. And so we can ask the question, how good is the angular resolution of a dish? So for instance, if I have two sources in the sky which are separated by a very small angle, will I be able to differentiate between them by using this dish? Can I add the signals of one source coherently, whereas add the signals of another source nearby with sufficient incoherence such that I diminish its contribution to the final detection I do at the feed horn. And so we can define something called beam shape. That's what I've drawn here in this figure. And so at bore site, you can think of this just as the sensitivity of this dish to different angles. So let's start with the bore site. At bore site, the dish has maximum sensitivity. And as you go away from bore site, its sensitivity falls down, right? And so essentially, we are asking the question, what is the width of this function? Because that width tells us how well I can resolve two different sources in the sky. And so that width is given by lambda divided by d. So lambda is the wavelength of light, and d is just the size of the dish. So that's the diameter of the dish. Now that's an approximation. The exact value depends on a lot of different factors which are related to how exactly the feed is designed and the dish is designed. But it is approximately given by lambda by d. So lambda by d is an angle in radians, and if sources are separated by more than this angle, then you will be able to resolve the two sources. You can tell one apart from the other. Now, at lower frequencies, the wavelength is quite large. It's about 2 meters, roughly the size of a human being. And let's suppose we build a dish which has 100 meters in diameter. That's a pretty big dish. It's not easy to structurally build a dish so big. But let's suppose we do that. And so the angular width is just given by 2 divided by 100. That's 0.02 radian. That's roughly about a degree in size. And so if sources are separated by more than a degree, this dish will be able to tell them apart. But everything within 1 degree of bore site, everything is going to be added on. The electric fields will just be added on in your detection, and you won't be able to say within the degree where the radiation came from. And that's generally not good enough for astronomy. So let's see what is good enough. So typically in optical astronomy, you would obtain a resolution about 1 second of arc. So that's 1 arc second. So let's say if we want the same, let's do that with at lower wavelengths of 2 meters. So 1 second of arc is so many radians here. And again, if I say that must be equal to lambda by d, lambda is 2 meters, I can work out that d is in the hundreds of kilometers. And clearly we cannot build a dish which is hundreds of kilometers in size. So we do the next best thing. And the next best thing is we imagine that you have an aperture which is hundreds of kilometers in size. We can't take over all the land within hundreds of kilometers. Even if we did, we won't be able to build detectors which cover the entire region of hundreds of kilometers. So we do the next best thing, which is that we build smaller detectors or antennas or stations in case of LOFAR that are spread over 400 or let's say hundreds of kilometers, but they don't cover the entire area. And so the idea here is as long as we have detectors which are spaced by this large amount in area, we will be able to get the benefit of the angular resolution which you get by having detectors spaced so far apart. But of course, we will give up something in return. And so what is that we give up in return? What we give in return is how pure or how clean the beam looks after beam forming. So let's suppose you had this whole aperture filled with detectors. So it's what you would call the filled aperture. You would get a sensitivity pattern on the sky that looks like this. So you have what is called at bore site, you will have a main beam. That is where you want to actually detect signals in that direction. But as you go away from the main beam, your sensitivity falls off. And that sensitivity is falling off because, again, when you beam form in bore site, all the signals coming from different directions which are here, they are not adding coherently. So they're all adding with random phases. And because of that, they're all averaging down, going to zero. But they don't go to zero exactly. How quickly they go to zero depends on how many of those copies of the electric field you add with random phases. And that is just given by the number of detectors or stations you have. So when you have an unfilled aperture, which is shown in the right, you have the main beam or the bore side, the width of that beam is very similar to the filled case. But of course, you have all of these what we call side lobes coming up. And that is just because you didn't have a filled aperture. So these things have not averaged down to zero fast enough for you because you didn't have enough detectors. And so that's the compromise we make usually in radio astronomy because we can't build such big detectors. We can't fill such big apertures. We try to have smaller apertures spread over a large geographical area. And that's basically what we essentially do in radio astronomy. That's what LOFAR does, what the VLA does, what many of the telescopes you have seen do.